Hi everyone, so in this video I want to just do a little introduction to proof by induction. And so to motivate this process, we'll considering the following example. Here's a statement. For all non-negative integers n, we have the nth derivative of e to the 2x equals 2 to the n times e to the 2x. And so here, n is denoting a non-negative integer since we're denoting this as an order of a derivative. So really what we're saying is we want to show the nth derivative of e to the 2x is equal to 2 to the nth power times e to the 2x. And so let's think about how we can prove this by looking at some cases for values of n. So we can organize our cases into a table on the left. And let's say we first consider the smallest non-negative integer, which it would be 0. So if n is 0, this means we are taking the 0th derivative, meaning we're not taking any derivatives. We get e to the 2x back, and that's equal to 2 to the 0th power. Remember, 2 to the 0, that for 2 to the 0, that equals 1. So over here, we actually do have 2 to the 0 since we have a leading factor of 1. So this checks for the 0th derivative. The 0th derivative of e to the 2x gives me 2 to the 0 times e to the 2x. And checking other values of n, if n is 1, then we can take the first derivative using the chain rule, and we get 2 to the first power times e to the 2x. And then we take second derivative, and here we can see that we don't need to retake the first derivative. So the second derivative would just be the first derivative of the previous derivative. And that gives us another power of 2. So now we got 2 squared times e to the 2x. So this checks out for the first 3 values. And now we can check n equals 3 to check a fourth value. And for this one, the third derivative, we can calculate by just taking the derivative of the previous second derivative. And that gives me another power of 2 that comes down. And then what we want to do is try and generalize this pattern because we want to prove this for all such integers n. And so can we prove the general case that this is going to be true for all such values of n? And that's where this proof technique, proof by induction, is going to come in handy. And so the picture that I'd like you to have in mind would be to think about like a line of dominoes that's falling over. And what we're going to hope to do today is show that if we can prove the first domino falls over, and if the first k dominoes fall over, then that's going to show that the k plus 1 domino needs to fall over. So let's see how we can formalize this process mathematically. So this process of induction is going to come in handy when we wish to prove statements such as show for all integers n, satisfying n is bigger than equal to some minimum value b, we'll call that the base value, that this statement p holds for all values of n. And so one way that we can prove this is using what's called mathematical induction. So let's just outline this process and then we can apply it to the previous example that we started looking at. So we start by first considering what is the base case for this integer n. In other words, what is the smallest value of n that we need to consider? And on the previous slide, we checked n equals 0, n equals 1, n equals 2, but the smallest derivative that we could possibly take would be the 0th derivative. So for us, our base case would be n equals 0 in that example. So this is equivalent to showing that the first domino falls down. Then we do the induction step, and that is we assume that this statement p holds for all integers that are greater than or equal to the smallest base case and less than n. So in other words, we're showing that we're going to assume that if the first k dominoes fall down, that's going to imply that they knock down all of the dominoes further on down the line. And this assumption is what's called the inductive hypothesis or the induction hypothesis, that being this statement right here. So when we assume that the statement holds for all integers k less than n, that's our inductive hypothesis, and then we hope to use that hypothesis to show that it therefore follows in the general case. And this process that we just outlined, this is what's called the principle of mathematical induction. So if you're reading some sources, you may see that there's a strong induction, a weak induction, different types of mathematical induction. And for our purposes, we're just going to consider them all under the same umbrella of there's one type of mathematical induction. Okay, so let's see how we can apply this process of mathematical induction to prove the example that we started considering. And that was, we've got for all non-negative integers n, the nth derivative of e to the 2x is equal to 2 to the nth power times e to the 2x. And so the first step in the process of induction is proving that we can knock the first domino over. And that's what we call the base case. So we would like to show that P, the statement P, is true for the smallest value of n, and that's what B is denoting. So our base step would have a base value B of 0, since that is the smallest non-negative integer. And so first we check the base case. Is this statement over here true when we plug 0 in for n? So these n's, we're going to plug in 0, and we're going to consider what do we get when we take the 0th derivative of e to the 2x, and we checked that on the table before that. Yeah, we get e to the 2x, which is in fact 2 to the 0th power times e to the 2x. So the base case, that checks out. And let's just see how we can write this up a little more formally. So that would maybe be some scratch work. But if we want to write this up a little more carefully, then let's use some complete sentences. So we would say, okay, if n is equal to 0, then the 0th derivative of e to the 2x is e to the 2x, and that equals 2 to the 0 times e to the 2x. And so our claim holds for the base case n equals 0. And so now we've got that the first domino is knocked down, and then we want to show that this is going to cause all of the subsequent dominoes to fall over. And so that part is called the induction step. And so this is when we assume that a bunch of dominoes get knocked over, and we want to show that if that happens, that's going to knock all of the dominoes further on down the line. And so how we can phrase that a little more carefully mathematically is we would say this statement P is true for all values of k bigger than or equal to the base value and less than some integer n. Then we want to show that the statement P is going to hold for values of n bigger than k. So in plain language, we might say this. This is saying all of the dominoes prior to the nth domino are knocked down. And then this is saying, therefore, it would follow that the nth domino is going to be knocked down. And that's enough to prove that, therefore, all of the dominoes would be knocked down. So in this example, where we're thinking about the derivatives of e to the 2x, our inductive hypothesis, what we are going to assume is that the statement P is true for a bunch of values. So in this case, we're going to assume that when I take the kth derivative of e to the 2x, I get 2 to the k e to the 2x, and I know this is true for 0. We already checked that, and we're going to assume it holds for all values of k bigger than or equal to the minimum value up to not including n. And then we want to show that it's going to therefore follow for n as well. So this is what we're going to try and prove in the inductive step. It's a conditional statement, namely, if this holds for a bunch of integers, then it's going to follow for integers that are greater than k. And so now let's organize our thoughts a little more carefully. So we know what it is that we're trying to prove in this inductive step now, namely a conditional statement that if this holds for all values of k bigger than or equal to 0 and less than n, then it would follow for n. So let's start by, first of all, defining what n is. So n is any value bigger than 0. And we assume our inductive hypothesis that this property holds for values of k, the integer k, that are less than n. So that's where we would start our proof. And then we work with what implications that would tell me. So if this is true, then let's try and prove this for the nth case. So let's write out what the nth case would look like. So that means we're taking the nth derivative of e to the 2x. And the trick here is you want to somehow use the inductive hypothesis in this proof. So taking the nth derivative is equivalent to taking the derivative of the n minus 1 derivative. And so now n minus 1 is an integer which is less than n. So it falls in the range of the values that we've assumed where this hypothesis is true. So since n minus 1 is less than n, we could therefore use the assumption in the inductive hypothesis, which is all of this is going to equal the n minus 1 derivative of e to the 2x is equal to 2 to the n minus 1 times e to the 2x. So this is the first n minus 1 derivatives. And now to get the nth derivative, we just take one more derivative. So the 2 to the n minus 1 gets pulled out. And then we apply the chain rule again to the e to the 2x. So we have this constant that gets pulled out. This constant comes down from the chain rule. And now we can simplify. And we've shown that for the nth derivative, yes, indeed, we do get 2 to the nth power times e to the 2x. So the inductive step also checks out. So on the last slide, I just want to show how you could write up all of this work in one nice, clean proof. So we started with the following problem. We wanted to show that for all non-negative integers n, the nth derivative of e to the 2x is 2 to the n times e to the 2x. So when we're trying to write our proofs, just recall that you should start, if you're not going to use direct proof, by indicating what proof technique you're going to use. So we are going to prove this using induction. And then we need to state what it is we're going to use induction on. So we're going to use induction on n, which is the order of the derivative that we are taking, applying to e to the 2x. Then we would use our base case. So I just took this, copied and pasted from what we had proven on a previous slide. So for the base case, we weren't taking any derivatives of e to the 2x, and therefore we got e to the 2x back, which is 2 to the 0 times e to the 2x. Then we could write up our inductive step carefully. And again, this is just exactly what we wrote up on the previous slide. And then we can conclude after proving the base and the induction step that, okay, using induction, we have proven that for all non-negative integers and that this property does indeed hold. So this is what the process looks like. For the quiz, I want you to focus on how you would set up the base and induction steps. And then in class together, we'll go through how we can actually execute those steps. Okay, see everybody in class.